So today's session is about finding out or being able to recognize handwritten digits. Okay, so how do we do that? Let's see how this session is going to cover. We are going to cover a little bit of introduction about data science, machine learning. We will have a little bit of understanding on what are prediction problems, classification problem, and clustering problems. So essentially, these are various types of machine learning or predictive analytics algorithms. So when you get into problem solving like handwritten digit recognition, you need to understand what kind of problem they are and what kind of algorithm essentially are used to solve those image recognition problems. Then we are going to cover how images are represented in computer terms. So obviously images are not stored as images as such in a computer, or image, or let's say for instance text is not stored in computers as text. They are all stored in various numerical forms. So we will see how images are stored, and then after that we are going to look at two different techniques for handwritten digits recognition. One is called support vector machine. It's a classification technique, and the next one is K-means clustering. It's a clustering technique. And before as we are using a classification technique and another clustering technique, briefly we also have to understand what those prediction or classification or clustering mechanisms are. Okay, so to have a little bit of introduction about machine learning, according to a Wikipedia definition, is a study of computer algorithms that improve automatically through experience and by use of data. It's seen as part of artificial intelligence. So machine learning algorithms build a model based on sample data known as training data in order to make predictions or decisions without being explicitly programmed to do so. It's quite a mouthful and maybe a little ambiguous as well for a beginner, if you are a beginner in machine learning or data science. So what it means is that similar to how human beings learn. So when we are children, we look at our surroundings and our parents, our relatives, our folks continuously keep us trained in terms of, okay, so this is a ball, or this is a house, or this is a cat, or this is a mouse, or this is a dog, etc., etc. So you absorb data around you in form of images and noises or sounds, etc., etc., and you are continuously being told as to this is this and this is that and this is that, and you keep on learning from those data. So at one side you are absorbing data from your environment, and on the other side you are being told what is what. Okay, so because you are seeing a cat, all right, so that's data coming to you, but you don't know it is a cat, so you need to be told it is a cat. So machines, I mean in machine learning or data science and predictive algorithm, or let's say for instance when we go more advanced in deep learning, at one side you will be the algorithms absorb data, and on the other side they have to be told what is what. So it's a learning process similar to how a kid learns. It's a learning process for the machine. So what is extremely important for, there are two things that are extremely important for this kind of algorithms, machine learning or data science algorithms. These two things are, one side is data and the second is algorithm. Okay, the learning technique is the algorithm and the data is what you learn from. So just like a child absorbs the data in his or her surroundings, similar, you have to feed the machine the data, and you have to tell this data means this and this data means that, and also you have to tell it the learning process, what learning process it has to use. Okay, now some of the uses of machine learning are, let's say for instance voice assistant. So voice assistant, what is voice assistant? How do voice assistants work? You have say for instance you have a restaurant table booking system. So what happens is that somebody calls up the restaurant. It's a voice assisted number. So if it is a voice assisted number, you call up the restaurant and somebody picks up, says hello, how can I help you? And then you say that, okay, can you book a table for me for 3 persons today evening at say 8 o'clock. All right, and you name the restaurant. So let's say, for instance, if it is a hotel and there are multiple restaurants, you name the restaurant in which the table has to be booked, and etc. Some information, basic information, and then the person at the other side books a table for you and confirms that okay, your booking is confirmed. We will see you at 8 o'clock. Now you hang up without realizing that all this while you have been talking to a voice assistant rather than a real person. So how does it do that? How do we create these voice assistants? We feed it a lot of data, and in this case for voice assistants, the data is a lot of conversations in that particular domain. So in that particular domain means conversations around booking in restaurant. So I mean, a conversation can be in n number of different permutations and combinations. No two persons are going to say the same sentence in instructing a person to book the table. Okay, so there can be n number of different conversations, different permutations and conversations of sentences that are used to book the table, and the machine has to learn from thousands and thousands of conversations as to okay, this can be a combination, this can be a combination, this can be a template, etc. So that's data, and it also has to be told that in this for this kind of instructions or this kind of sentences, you need to take this action. All right, so this is how a question looks like, and these are the possible answers. So all this kind of data are fed right into something which does natural language processing. So when this learning process is over, the voice assistant is equipped with the learning that a normal human being would be, in case the normal human being is told how to kind of deal with that kind of situation. In the same way, the machine will be now ready to with the ability to answer your question. So these are normally done in a combination of natural language processing as well as deep learning techniques. Say for instance, stock price prediction. So how do we how can somebody predict stock prices? I mean, let's say for instance there is a super expert stock analyst, and this person can look through a stock's trend over the last few years and can tell you as to okay, this is going to be the approximate trend of this particular stock for the next 6 months, right? Now how does this person able to make that kind of prediction? A human being, by making an understanding about the stock price over the data that is presented to him or her pertaining to that stock over the last few years. Okay, and then he or she applies some analytical technique that is also acquired learning through various expertise in the stock price analysis domain. So different types of learnings are an amalgamation of different types of learning results in this person's ability to be able to tell you the stock price trend for future. Now the same thing has to be fed into a learning algorithm for a stock price prediction scenario in machine learning. Okay, so now this can be a prediction problem, but in a normal naive kind of machine learning prediction algorithm is not going to be able to predict stock price trends perfectly. We use different techniques like in deep learning, especially for this kind of problems, we use something called recurrent neural network, okay, which can memorize trends of the past. So these are some of the examples of machine learning. So you see that data is at the core of it, and learning is another very important aspect of machine learning. Combination of these two creates smart machines of machine learning or deep learning or data science. There is a difference between traditional programming and machine learning. How are they different? Some of the answer lies in the explanation of the previous slide. In traditional programming, normally what happens is business comes to you and business tells you that okay, I need this set of business rules encoded in a program, and you write that program and give it to me. All right, so the rules that have to go inside the program are already known. Okay, so you understand the data, you know exactly what is expected in the data that is going to be fed to the program that you're going to write. You know the attributes, you know the characteristics of the data, and you know the rules that data has to go through. So that is known, the rules are known, and those rules are translated into a program. You write the program and you implement the program in your live system, production, etc., whatever you call it, and then you feed the data, your expected data, and that produces results. So your rules, the most important thing is your rules are known beforehand. They are deterministic. Now in machine learning, it is completely different. The rules are not known. Okay, whereas we work on patterns in the data. All right, so let's say for instance we take the case of a regression problem. So what is a regression problem? We take an example. House price is commonly used, a house price prediction problem, or a car price prediction problem. So let's say take the example of a car price prediction problem. So in a car price prediction problem, it's a scenario with a car sales agency. So they deal with resale of a lot of old cars. So how do they determine the price of those cars? They have their analysts or agents who are experts in second-hand cars, and those agents are called to inspect the car that has come for resale. And they inspect the car and say that, okay, fine, this is this many number of years old, and this has this big an engine, this cc capacity, and this much horsepower, and the length and the breadth and wheelbase. Okay, so yeah, so you have a historical transaction where there is a those transactions are that of a lot of car sales, and each of those transactions have the car attributes. So year of build, so that gives the age of the car, and the cc capacity or the horsepower, then say for instance the mileage, the fuel mileage, then you have the wheelbase or the ground clearance, or say for instance the length of the car, so how big the car is, the brand, etc., etc. So these are attributes of the car. And on the other hand, you have the sale prices, the historical sale prices against each of those cars. So given this scenario, the owner of this car dealership comes to you. You are a machine learning engineer or a data science engineer, comes to you and says that, okay, so we want to automate the process of determining the prices of our cars. Okay, so if we want to do that, can you automate that? So what we'll do is, so we'll use something called the linear regression algorithm. All right, and feed the historical transactions to the linear regression algorithm, and we are going to predict so it's going to learn the patterns of the car attributes and the relationship of those car attributes to the sale prices historically. And then in its mind, in what it produces as a model, it's called a model. In the model, it encodes the relationship between the attributes and the prices. Okay, in a deterministic situation, you already know what are the rules from those attributes to the prices. But in this case, it's not a deterministic situation. You are not sure, and there is no definite pattern. There are approximate patterns of how these attributes influence the price. There is an approximate pattern. There is no definite pattern or no deterministic pattern. So when you create the model from a non-deterministic pattern, an approximate, that has to be done through a linear regression machine learning algorithm. So when that is done, you feed new data of car attributes to the linear regression model, and that model, from its knowledge from the historical information, can predict a approximate sale price that you have to use for this new car. Okay, so this is how it is, how the difference of traditional programming and machine learning. Okay, so quickly, there are a number of different types of machine learnings. or data science predictive algorithms, supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Quickly, how they are. So the case that I have mentioned, in case of the linear regression problem just now, you feed the historical data to the learning algorithm, the linear regression learning algorithm. Now there are two parts of the data. One is a set of predictor variable, which are the car attributes, and a target variable, which are the car price. So in the learning phase, you feed in the entire data, including the predictor variables and the target variable, in this case the price. In case of the testing phase, or in the live phase of the model, you do not feed the target variable, you feed in the attributes, and you expect the target variable back, the target value back. Okay, so in this case you have labels or target values present in your training data. Okay, so when this is the case, it is called supervised learning. However, there are other types of learning algorithm where you know that there are definite patterns in the data, however you cannot pinpoint a target value. So let's say, for instance, in Amazon wants to segment their customers based on their purchasing behaviors. Now what is purchasing behavior? There is no such field called purchasing behavior. The purchasing behavior is a combination of a lot of different attributes. Okay, it can be time of purchase, it can be the gender of the person buying, it can be the kind of goods that person is buying, it can be the amount of the range of amounts of money that the person is spending, it can be number of items that he or she is buying, etc. So it's a combination. So but in this case there is no definite target variable. So in those cases it is unsupervised learning. A semi-supervised learning is a bit of combination of both of them. So what is semi-supervised learning is, let's say for instance, Google Photos. So in Google Photos, what happens is that when you feed it a picture, you first time it is going to ask you to label the pictures. So one picture you label as me, or somebody say Prakash, or somebody Shruti, etc. So you label the pictures, identifying, and Google Photos knows that this is this person. So subsequent photos will be, so that's a supervised learning. Subsequently, it is going to learn to identify other persons based on your initial feedback. But sometimes it is going to come back and ask you that, can you re-identify this person? Okay, because I'm not sure yet, or I want to be doubly sure. So it continues, I mean, periodically it comes and asks you that question. So this is a case of semi-supervised. Reinforcement learning is a completely different beast altogether. It works on a, it is applied on cases like computer games. So the machine plays a game with a person possibly, or another machine, or say for instance self-driving cars. So these are used in situation where you have to find an optimum solution based on a reward and penalty basis. An agent works, the agent is the learning algorithm, and the learning algorithm, based on a reward and penalty basis, tries to find the best optimum solution. So these are some of the classifications of algorithms, learning algorithms, or machine learning algorithms. Now the reason we wanted to discuss this is that giving you a brief idea in the before we go into the actual algorithm, actual handwritten recognition. Now quickly, some idea about what are the steps that we normally follow in data science machine learning projects. We determine a problem statement. So in this car sales car price detection problem, so obviously our goal or the problem statement is that we want to automate the process of finding out car sales values for second-hand cars, because we have the historical transaction where we have the type of cars, all the attributes, and the sale prices, so we know from beforehand. So if that data can be used to teach and create a model, a linear regression model, then that linear regression model can automatically generate the car prices. So a problem statement is important. Second is you have to collect data. So in this case you need to be sure, I mean, if the automation for car price detection has to be done, then you need to have all the historical transactions, and historical transactions also need to be in good order. So it cannot be that every piece of transaction will have some missing values, etc., and nothing is in order, and sometimes the car size is missing, or the ground clearance field is missing, some transactions there is no brand mentioned, etc., etc. So the data acquisition, data quality, etc. are important. So then you get into analysis and do a feature analysis and find out all pieces of data are in order, and do you have to create new features, etc., etc. So data analysis, pre-processing of data, data correction, data cleaning, etc., etc. all those steps that you have to undertake. We are not getting into detail. Every type of algorithm will have a need of data to be presented to it in a certain format, certain template. There are certain expectation about the data by each of the algorithms, and based on those expectation of the algorithm, the data analysis and data pre-processing have to be done, and it is also aligned with the problem statement. So based on the problem statement, you have to select what kind of data goes into the learning algorithms. There can be certain pieces of data in your in the data set that you have acquired that are not required for creating the model that you have to create for your specific business problem statement that you are solving. So those steps have to be done, and then you have to you have to do a model selection. So there are we mentioned that there are different classes of algorithms. There are prediction algorithms, there are classification algorithms, supervised models, and unsupervised models, etc. So you need to find out what is the right model for you, right learning algorithm for you. Okay, and then you go through the training process. So train the model using the learning algorithm and create the model. Okay, then you go through certain steps which are called model optimization. Model optimization essentially is using various hyperparameters and using various validation techniques or cross validation techniques, etc. Finding out the optimized model. Okay, it may also involve feature tuning or feature engineering in the process of model optimization. And then the last is your deployment of the model in production, and monitor and iteratively keep it up to date. Right, so these are the steps of machine learning project lifecycle. Now we come to our specific problem for the session, which is handwritten digit recognition. Now before we get into the algorithm, we need to understand how images are represented in computers. Now images are represented not as images inside the computer, not stored as images in the computer, but they are stored in the combination of numbers. So if you look at these images, okay, so this is a black and white image. Now black and white images are, or any image for that matter, even if it is a colored image, but we are taking this case of black and white image. It's formed of a matrix of pixels. So each of these tiny boxes are a pixel, and each pixel has a color, okay, or has a shade, a grayscale shade, right? Now each of these shades are different, and they are represented by a number which is in the scale of 0 to 255. It's a scale of 256 numbers. 0 being black, absolute black, and 255 being white. Okay, and all the grayscale values represent various shades of gray, starting from white to pitch black. Okay, or rather starting from black as 0 to complete white, which is 255. All right, so if you look at the second image, where each of these tiny pixels or pixels in the matrix, image matrix, are filled up with those values. Okay, so let's say for instance this particular one is almost black. It's not black completely, and if I can read it clearly, it says 5. So 0 being complete black, 5 is close to almost black. Okay, so let's say for instance take another one, this one, this is or this one. So these are numbers of 235 or 237. So these are very close to white. So you can see that a slight tinge of grayishness, but it is almost white. Okay, and this particular one is white, completely white. This is 255. All right, so any image in the storage of a computer are stored like this, matrix of numbers. Okay, they are not stored as images, they are stored as matrix of numbers. So this is to give you an understanding of how an image is stored. So this is a shade card of the computer. So pitch black is 0 and complete white is milk white or whatever white you call it is 255. So that's a range of values for grayscale values. Okay, now the input that we are going to take for our case is going to be a data set called MNIST data set. It's a publicly available data set, and this data set is actually a set of this matrix which represent handwritten digits. So it essentially represents this image. All right, it's the original MNIST dataset has about 60,000 examples for training and 10,000 example for testing, but we are not going to take the full MNIST dataset. There are smaller versions of MNIST dataset available which are even smaller. So in our case, the dataset MNIST dataset that we are going to use, it's going to be comprising of about 1700 handwritten digits. Now there are going to be and they are singleton digits, so starting from 0 to 9, and you can see some samples of handwritten digit examples. So okay, so if intuitively you can see that there are some patterns. Okay, and with your idea now as to how images are represented as matrix of numbers, you can understand that okay, so if that is how the numbers are stored, the images are stored as pixels of or matrix of pixel values, grayscale values in representing pixels, then in the just like we can see the pattern visually of the digits written like this, we will be able to see some kind of pattern in the matrix as well, matrix of grayscale value numbers. Okay, so intuitively you can realize that these numbers will actually represent some kind of pattern in the number matrix as well. Now in MNIST dataset, one important characteristic is that each of them are 8 by 8 matrix of numbers. So let's say for instance if I go back, this is not this image is not a 8 by 8 matrix. This is like 1 2 3 4, something like 15 by 25, something like that. Okay, 15 columns and 25 rows. Not exactly correct, I haven't counted, but something like that. Not 8 by 8, but in case of MNIST dataset, each digit is represented by a 8 by 8 pixel matrix. Okay, all right, so with that understanding, we are going to look at two techniques. One is classification technique called support vector machine, and therein there is another technique that we are going to use. It is not exactly going to give us the perfect answer of what each digit represent, but it is going to give us some intuition, and we are going to see how it is going to give it by using a clustering technique called KMeans. And if you remember, we've given one example of clustering technique on customer segmentation of the Amazon, or let's say an e-commerce site for customer purchase behavior. All right, customer segmentation based on customer purchase behavior. All right, so we are going to use this technique, but before we get there, just as a recap. All right, so we'll cover a couple of more slides before we get into the code. Just a little bit of intuition about support vector machine. In our course, we go in much more detail. Support vector machine is a class of is a part of a class of algorithms which are called classification algorithm. Now, classification algorithms are used in solving problems related to classification. So, one example is, say, the MNIST data set. So here in this case, what is our goal? Our goal is, given a pixel matrix of 8 by 8, we need to identify whether it is 0 or 1 or 2 or 3 or 5 or 9. Okay, so it's a classification problem. Another example can be, we have say in a healthcare situation, we have the case of, in a hospital, they want a system, they have a system wherein patient diagnosis data are collected, and then a doctor sits down and kind of evaluates based on those values of those parameters as to whether this person has a disease, a heart condition or not. So it's based on the blood pressure level, ECG reading, say your cholesterol level, LDL level, etc., etc., sugar level, fasting sugar or non-fasting sugar, etc., etc. Number of parameters are measured, and then based on those values, a doctor determines whether this person has a heart condition. But this comes from pure experience, and if we can automate that experience, and we now know that with machine learning algorithms, they are called learning algorithms. So a machine learning algorithm can also learn those patterns, and just like the doctor, it can give the classification as to this person has a heart condition or not. But before it does that, you have to teach it, and it has to learn, and it has to learn from historical data, where you have the health parameters of specific individuals, and the classification that this person had a heart condition, represented by 1, or did not have a heart condition, represented by 0. So this is also another case of classification problem. So support vector machine is one such classification problem, which uses a method in which given sets of data, let's say in a two-dimensional surface, or in a two-dimensional data, you have a set of data here and you have a set of data here. In reality, you will never have two-dimensional data, you will have multi-dimensional data, but this is used for just for understanding's purpose. In the support vector classification algorithm tries to find out the separating line which stands in the midway of a path that it can create, which is going to be the widest path separating two groups of data. Okay, so I mean, I know that it may not make a lot of sense right now, but in our course, so we go into much more detail as to how the support vector machine actually works, and how it does classification, etc., and what kind of parameters it uses, etc., how to optimize it, and so on. So that is support vector machine. We are going to see one example, one of the techniques to classify our digits. And the second technique is going to be, say we have these data sets. Again, we, for example's sake, for understanding's sake, we take a two-dimensional data, and we see that okay, there are clusters. Okay, in the case of case that I have mentioned to you, that you have customer transaction data, and Amazon wants to know, fine, I want to segment my customers based on their purchasing behavior. Now that's a vague statement to make. Do I have three different sets of three different types of patterns in the customer purchase behavior, or do I have 10 different patterns in the purchase behavior in the data? Okay, I don't know that. All right, and there are ways and means of finding that out. The optimal number of patterns that we want to, or optimal number of clusters that we want to find out of this clustering exercise. So with that, if you see that this is our data, the input data set, we can make it in two clusters. We can segment this in 3 clusters, or we can also segment this in 4 clusters. Okay, so this clearly is a case of an optimized, the optimized number of clusters is 4. So there are algorithms. The K-means algorithms uses a mathematical technique which revolves around a concept of a centroid that are initialized randomly, and then the centroids are optimized based on the number of K, which is the number of clusters that you start with. And using techniques like cross-validation techniques, it can come to an optimal value of K, and it can give you the K number of clusters from your data. Okay, so that's K-means clustering, and you can solve problems like customer segmentation, which are not supervised learning in our case. All right, so these are the two techniques that we are going to use. Just before we go into the code, as I mentioned that we have two courses that are coming up. One is on data science and predictive analytics mastery, and the second is machine learning mastery. These are compact courses for working professionals. They are 2 weeks long, each to be hosted on each working day. The timings are flexible. They are morning 7 to 9 and before you start your office, or evening 6 to 8, and of 20 hours. In these courses, we teach you on a project based way as to the different techniques of data science and different techniques of machine learning mastery. Machine learning mastery focuses a lot on learning a number of machine learning techniques and machine learning algorithms, whereas data science and predictive analytics teaches you machine learning algorithms, not so many of them, but focuses a lot on data analysis, exploratory data analysis, statistical techniques, visualizations and all. So you can go to our website and find out more about these courses. Some of the things you will not go into the course structures, but we'll mention a couple of things to you so that you are aware. The courses also include three free sessions on Python. If somebody is not familiar with Python, they can attend our free sessions and familiarize themselves on Python. We are also going to we focus a lot and spend a lot of time on creating courseware that are exclusive to us, and we create a lot of ebooks for our students. And as part of this course, you are going to get 6 ebooks covering the concepts that are being taught in the course. And mind you that we are going to teach these concepts to you, both data science and machine learning, on a completely hands-on project-based way. Okay, and we will also give you one additional session on interview preparation after the course is over. With that, we will now jump onto the coding. All right, so first we will go through the SVM classifier. So we have mentioned that we are going to use the SVM, or a support vector machine classifier. So we have spoken about the data, so I don't have to explain to you. So essentially the data set is publicly available, and then the data set is part of the sklearn or scikit-learn machine learning library. So you have to, so this is Python, and I am using the Anaconda Jupyter notebook. So if you want to practice, you can download Anaconda and you can invoke the Jupyter notebook. It automatically installs Python 3.6 for you, 3.6 or 3.9 for you. So that's going to be already available, and I'm using the Jupyter notebook from Anaconda for doing this. So the dataset, the MNIST dataset, is part of the, as I was saying, part of the scikit-learn machine learning library, and you have to import the dataset by using this statement from sklearn.datasets, import the load digits, and invoke the load digits function to actually create this digits data object. Now, what is the digits data object? It's actually a Python dictionary. All right, so if you know Python or interested in Python, Python has a number of different internally available composite data structures, or collection data structures or data objects, and dictionary is one of them. Dictionary, the characteristics of dictionary is that dictionaries are stored in key value dictionaries get represented in key value pairs. So it's a key value pair that is getting created. So one of the key which stores our images is the data key, and another key that is important to us is the target, which store corresponding images or corresponding digit numbers. So it stores 0, 1, 2, 3, 4. So what happens is that the first array in the data set data key, it's an array of arrays. Actually, the data is stored in organized in the form of an array of arrays. Now the first array represent 0, the second array represent 1, the third array represent 2, and so on, and it goes until 9, and it comes back from 0, 1, 2, 3, 4, etc. Then the other you need to do a little bit of play around to find out the exact or understand the exact structure of digits, the low digits data set, or the MNIST data set actually it is called. And the third one that is important to us is images, the images key, and that is also organized in terms of array of arrays. Now how many number of digits each image of a handwritten character is going to be comprising of? We said it is a 8 by 8 pixel matrix. So there are going to be 64 different numbers representing each digit. These arrays here within the data key, and the data I said is array of arrays, each of those nested arrays are of length 64. So these are flattened matrix. So there are 64 number of digits here. In contrast, if you look at images, these are array of arrays, 3 levels. Okay, and each array is of 8 length. All right, and array of arrays, each array of array represent 1 digit. All right, so images organize the digits in the form of 8 by 8 into the number of digits our data has, which is about 1700 something. Okay, so that is the difference between data and images keys here in this construct. Okay, so there is one trick that I'm going to play here. So digits data, so we are invoking this key, and we said that these are arrays of 64 length, because each of these are representing a digit. Okay, and 0 is pointing to the first element in data. Okay, so now I'm going to make it a little bigger for your benefit, and you tell me, by looking at this 8 by 8 pixel matrix, do you see 0? So this is what I was referring to as intuitively, if the pixels have contain the grayscale values, then you can relate those numbers, the numbers in the matrix also visually, and recognize that what numbers are, what matrix, pixel matrix are representing what numbers. So you can see this pattern here, right? So the sides are 0. Okay, so because for a 0, the it's in the middle, and the sides have to be blank, no color. And here there are numbers, and there are high numbers over here, and there are smaller numbers, and in the middle there are zeros again, because of course 0 has blank or white in the middle. Okay, so this is how digits are stored. So it's almost intuitive that to figure out the numbers from the data that you see, the image matrix that you see, right? Okay, so these are all fine. I have also tried to, you see here, I have reshaped, because this key data store the images in a flattened format, a flat array of 64 numbers. I had to reshape it to 8 by 8 matrix just for visualizing it. But images already is a 8 by 8 matrix. Okay, so I didn't have to it's the same data, it represents the same data, but I didn't have to reshape it to a 8 by 8 matrix. We also look at what the target key holds. The target key holds the numbers that each of them represent. So if this is 0, the first value of the target is going to be 0. So if you see 1, this one, so this is an example of 1. So you can see 1 right here in the middle. There are bigger numbers, and you have this slant which is at the top of 1. So it looks like a 1. So that is the second number. So here in this, that is the corresponding target value. Okay, so I'm showing you this because you need to understand the data, and because if you have to use it for your training purpose, you need to understand the data and find out which data, whether we may use the data key or the image key for training purpose. Okay, so this is a simple code used for printing out the number. There is this function Python offers, which is ImShow, and we feed the images data in it in a for loop, and it prints out all the digits for us. Okay, ImShow displays images from pixel matrix. Okay, so that's what ImShow does, and we do it in a for loop, and we get all the digits that we are having in our data. All right, so next one, we will quickly skip over this part, and we will skip over this part, and we will come to this. We are going to use the support vector machine algorithm, which is this SVM SVC function, and the SVC function, or the support vector machine classification algorithm, is going to learn from the data that we feed to it, and it is going to understand the pattern from the data. So what is our data? As I mentioned before, when you teach an algorithm, especially in supervised algorithm, in this case we have a supervised algorithm, you have two parts of the data. One side is the set of predictor variables that influence a target variable. So the other variable is the target variable. So what is the target variable? The target variable are the digit numbers, which are 0, 1, 2, 3, 4 to 9. And the predictor variable in our case is your data side. Okay, so either the images or the data which have the entire pixel construct of the images. So at one side you have the pixel construct 8 by 8 matrix, which are essentially 64 numbers for each image, and against each set of 64 numbers you have the target values, which are, okay, for this particular pixel construct the target value is 1 or 2 or 3 or 4, something like that. Okay, so these are the two sets of values that we are going to feed. So with this statement, we create an object of support vector machine type, and then we fit it. Fit actually invokes the training process, and it leads to the trained model. These are the two sets of data that we are feeding it. Okay, now what are this data? Exactly what I mentioned, that main data, which is this part, main data is coming from this. We have assigned the entire set of pixel matrix values, about 1700 something of them, into this array called main data. So you are feeding main data to it. How many values or how many images that you are feeding to it? You are feeding 1500 values. We haven't taken the entire set. We have taken only the 0. I mean, if you leave the first index blank, that means 0. So 0 to 1500 images we have taken, and we are feeding it as the influencer variables. And the second parameter of the fit function is your target variable, which is the target value, which is coming from the targets construct. Okay, so it learns from this two sets of data, and then the next thing that we are going to do, and these are done in a very quick and dirty fashion. I mean, just for example, these are done in very quick and dirty fashion, but in real life cases there are going to be a lot of analysis about the data, exploratory data analysis, data cleaning, data feature engineering, etc., etc. And there are a lot of tweaks that we have to do in terms of I mean, this is a toy case, but in real cases we have to do a lot of tweaking using these hyperparameters, because this may not be the optimum hyperparameters based on which generalization, so there's the concept of generalization, a model can be good or bad and able to predict future values based on generalization levels. So we predict, so this is a toy case, we predict means that okay, now I have got my model. Which is the model? SVC is the model, this is the model. Okay, so we have created the SVC model object, and then we have fit it, so that means it has gone through the learning process, and now SVC is the prepared model, and we can use the model.predict function using new set of values to make the predictions. So what is the difference between the prediction step and the training step? So this is the training step and this is the prediction step. In training step, you are feeding it the influencing variables, which is the predictor variables and the target variables. In predict stage, you are feeding only one set of value. You do not have the target set of values, you presume. Okay, in our case we have, but it's a testing that we are doing. So in this case we are feeding it new data. So what is the new data? So I've mentioned to you that we have taken only 1500 0 to 1500 instances of the images. For testing, we are taking all those instances from 1500 to 1756 or something like that. So those many number of instances. So this data and this data are different. The predictions is an array which is going to hold the predicted values. What are the predicted values? The predicted values are equivalent to the target. So for each of these image constructs or pixel matrix or flattened pixel matrix that are there in main data, predictions is going to hold the, whether it's a 0, whether it's a 1, whether it's a 3, whether it's a 7, or whether it's a 9. Okay, so that's what it is going to. Now the next thing that you want to do is to check whether the prediction from the model are indeed correct or not. So the correct values that you already know of are there in the targets construct, the targets array, so you know that, and predictions is what has been predicted by the model. So now fun, let's see whether it has predicted correctly. So zip and list, it actually couples these two values and makes it in the form of tuples. Tuple is another collection object in Python, and you see these are the predicted values on the left hand side, and on the right hand side you have the actual values from your data, and in all cases it look right. There are some mistakes it has made, we'll see in a bit. So here what we are creating is something called confusion matrix. Confusion matrix is again another concept for evaluating performances of classification algorithms. So essentially what it means is that on the we've also created a heat map. Okay, it's confusion matrix is a kind of textual construct, but we have created a heat map out of that. So in the heat map it is visually more appealing, so I'll explain. So what it does is that from your prediction data and with the comparison with the actual data, it has figured out how many it has got correct. Okay, on the along the x-axis, if you perceive this as x-axis and this is a y-axis, along the x-axis you have 0 to 9, so these are the digits that you are predicting, and along the y-axis also you have the same values. Now what it means is that there are 26 zeros, these are the actual values and these are the predicted. So this is the actual axis and this is the predicted axis. Okay, 26 number of zeros which were in actuals are predicted correctly by the model. However, one of them has been predicted as 1. That's a little strange. Okay, see some else. 7 and intersection of 7 and 7, 30 number of 7s in actual are predicted as 7, which is great. Let's see this one. 3 number of 4s in actual are predicted as 9. Now you see the problem here. The problem is sometimes in handwriting 9s look like 4s or 4s look like 9, and the same confusion that the a human being may have, the machine also had. Okay, 4s and 9s are very near in its in their construct when you write it. 3 and 8 are also similar in writing. Okay, you close the loops of 3 and you get 8. Now there are 4 mistakes that the machine has also made. Okay, so 3 in actual predicted as 8 by the model, and there are 4 occurrences of that. And there are a couple of cases where the digits were 3 in actual but predicted as 5 can also happen. Okay, you close one loop and remove one loop of 3 and it may look like a 5. So you know that intuitively the kind of mistakes a human being will make are being made by the machine also, and this is called a confusion matrix, and this confusion matrix is generated automatically by the confusion matrix function, and you get a clear indication of where it has gone wrong, where it has made a mistake, and what has come fine. If you print a classification report, and the classification report is from the matrix library of scikit-learn. If you print the classification report using the predictions and targets, it'll tell you that we are 95% correct in predicting handwritten digits. Isn't that wonderful? It is. Okay, however, mind you, this measure of accuracy is not the ultimate measure in all kind of classification cases. Okay, and there are certain situations. If you use accuracy as the performance measure of classification techniques, classification solutions, you may go horribly wrong. So there are other classification matrix that are like specificity, sensitivity, recall, etc., which are more useful in certain scenarios. All right, with that we will move over to another technique. Okay, in the next technique we are going to use a clustering algorithm. Now why are we going to use a clustering algorithm? I mean, when we defined the problem of handwritten character recognition, it was clear that it's a clear case of classification. Okay, so you have got a pixel matrix in your data, and you have got you have to recognize the digits. You are teaching the model through the combination of the pixel matrix, the available pixel matrix, and the target values, which are zeros and ones and twos and nines, etc. Okay, so it's a clear case of classification. Now the clustering is not going to output the exact number, but it is going to give you an intuition of how the patterns of each of the digits are distinct from each other in a visual manner. Okay, it's not going to tell which data pertain to, or which pixel matrix pertain to say 0, or which pixel matrix pertain to say 5, or which pixel matrix pertain to 9. It's not going to tell you that, but it's going to tell you visually, okay, this is the visual segmentation of all this data in a two-dimensional surface. So that is what we are going to look at. We are not going to do the clustering because, but this is for fun. This is intuition of segmentation of data. Okay, so we are going to use the same data set. We are not going to look into the analysis of the data here. Instead, what we are going to do is we are going to, this is how the data is. Fine, so we have got an intuition about the data in the previous technique, and we are not going to go over that. We are going to come to a section in which we do something called scaling. Now in a lot of cases for machine learning algorithms, if data exists in different scales in their features, it does not perform very well. Okay, attributes or variables which have data in higher scales get more weightage as influencing variables in the model, which may not be correct. Okay, so that is why we use a process called we use a technique called the scaling technique, in which what we do is all the values that you have in different attributes or variables in your data are scaled to or fit to the same scale. What do we mean by that? So what are the features or what are the variables in your data? So this is your pixel matrix. So how many pixel values each of your image comprise of? 64, 8 by 8, 64. So how many variables or how many fields each of your data instance or observation has? 64. So that is what we are seeing here. What we have done is we have converted the data into a data frame format. Again, data frame is a very useful construct data object, collection data object in Python. That is part of the pandas library. So we have converted into a data frame, and you can see that pixel 0 to pixel 63 are the variables. So each image has 64 variables. Now if you look at them, some has all zeros. Okay, some are in the range of 0, 5, 9, 1, 8, etc. But some may sometimes go to 13, 14, or sometimes above 100, etc., or 200, etc. Now when the model is trying to build a model, or the learning algorithm is trying to build a model, which by looking at variables which have zeros and ones or twos or threes in it as its values, vis-a-vis other fields which can also have 255 or 200 or 150, etc., that creates a bit of disparity. Okay, and the model can go wrong. So we go through a scaling process. We are not going to explain the scaling process. We use a library called minmax scaler and use a minmax scaler function to do the scaling. So what happens is that each of your values are fitted within a scale of 0 to 1. Okay, so now you see the converted values in the images, they are within 0 to 1. Okay, so once all the values are fitted within 0 to 1, the scaling process is complete, and now we are going to do the model training. Now what are we going to use for model training? We are going to use the K-means clustering algorithm. So same process as we followed in the SVM algorithm as well. So we say K-means. How many clusters do we have? So K-means clustering, we said clustering process from our, if you remember from our PPT slide on clustering, there we say that we have data, and the data have clusters. Okay, clusters are data with similar patterns that we do not know of, and the clustering algorithms are used to find out those patterns. Now in our case, we do know how many such clusters are going to be in our data, 10, right? 0 to 9, because we are our goal is to find out one among the 10 digits. All right, so we already know the value of k, so we tell K-means that, okay, based on the similarity of the data that I am giving to you, which is my images in the form of pixel grids or pixel arrays, find out 10 patterns. Okay, now K-means doesn't know that you have given it the image data of 10 different digits, right? What is going to be fun is seeing if K-means come up with the clusters that you see expect to see within your digits, all right, within your image data. So that's what we are going to do. Now it does that. Okay, so when we say model fits with our data, so this is our image data, with after scaling, it creates 10 clusters. All right, and those 10 clusters are stored in model 10. Now this 10 clusters, how many, again going back, how many variables did we have in the images? 64 variables, right? Going back, if you see your metric structure, image pixel structure, each of the images have 64 variables, 64 different numbers in each of them. Now can you, I mean our goal in this case is visually showing you that there are 10 clusters, okay, like this. Now if you have 64 different variables, can you reasonably portray that in a two-dimensional surface? Ours is a computer screen. It's a two-dimensional surface. At most we can portray 3 dimensions, okay, visually, but beyond that it is not possible to understand data if we portray in any other higher dimensions. So what we now need to do is we want to see the clusters in the data that KMeans has created. However, we need to find a way of portraying the data in a two-dimensional surface. So 64 dimensional data I want to visualize in a two-dimensional surface. That is a tricky bit, okay. However, there are mechanisms or techniques which are called dimensionality reduction technique, like principal component analysis or TSNE, and we have used a TSNE, which reduce the dimension of multi-dimensional or higher dimensional data into the number of dimensions you want it to be. Okay, in this case, and it's by all means, by any means, it is not losing information by doing that. Okay, there are mathematical techniques in which TSNE is applying on your 64 dimensional data, so that when it gets converted into a two-dimensional data, and it's not selecting two different variables from your existing data, it's creating two new dimensions or variables altogether new. The information, the variance information that is there in your 64 dimensional data are still retained. May not be 100%, but maybe 90%. Okay, so there are mathematical formulas which are applied by TSNE to convert 64 dimensional data into two-dimensional data. Now if you have a two-dimensional data, you can definitely project that in a two-dimensional surface in the form of a graph. So what are we going to do is that, okay, so fine, so what we have after fit transform of your scale data, it is going to create an array of two-dimensional data from the 64 dimensional data which are already scaled, and put that there. Now what we are going to do is we are going to plot that two-dimensional array into a two-dimensional plane. So we are creating a matplotlib scatter plot. So this is a scatter plot, a conventional scatter plot, and we are presenting that data. So the first dimension in the array is a first dimension. So both of them are compressed into two dimensions. So 0 being this is the first dimension and this is the second dimension. So when it's plotted on this, and we use a color scheme, all right, and the color scheme is based on the predicted labels. So it's coming from outside, and what are this coming from? It is coming from this model, and the labels attribute of the model, your KMeans model, provide the labels. And what are those labels? The labels are 0 to 1. Okay, so that means this color scheme is based on the labels. So whichever data pertains to the corresponding label are plotted here, and each separate label, so ones are given a particular color, zeros are given another color, and twos are given another color, and nines are given another color, etc. So in all, if you count, there are 10 colors available here, and you can see the purpose of visualizing your data in the scatter plot using the color scheme here is that we see there are different clusters. Okay, now here is a mistake, right? So we have seen from our confusion matrix there are certain cases where there are mistakes, that 3 is understood by the model as 5, or 8 is understood as 3, or 3 is understood as 8, and there are in the clusters you will find some of those mistakes. So these are some yellow dots in the green cluster, or these are purple, deep purple dot in a green cluster. So these are the mistakes that are coming out of the clustering. Okay. Okay, so this is how we see that intuitively there are different segments that are created by a clustering algorithm. So this is a glimpse. All right, so this brings us to an end of this workshop. If you